for coming. Today we have a talk by Maria Nocchi, who is going to talk about high energy amplitudes of AdS string amplitudes. Thank you very much for accepting our invitation, Maria, and please go ahead.
Thank you. Thank you for the possibility to share my research today with you. This is going to be based on some work made in collaboration with Luis Fernando Aldeo, who's my supervisor in Oxford, and Tobias Hansen, Clement Virali, and Shinanzu over the past couple of years. And I will be focusing on these two papers, which are about high energy limits of the AdS string amplitude. And just as a brief outline, I'll start by giving some introduction and motivation behind what we are doing, and introduce you to the interplay between string theory and number theory, which is a very well-established interplay in flat space, but we can also say something about that in AdS. And then we will be focusing on the AdS Virasoro-Shapiro amplitude. And in the second part of the talk, I will finally present our results for the high energy limit first, and then we will focus on the Regge limit, which was our last paper in this program. Okay. So first of all, why would we care about string amplitudes in AdS? I think in physics, we are used to the concept of scattering amplitudes as an encoding probability for a certain process to happen. They are very strong predictive tools, so we can give some predictions for our theory and then test them by looking at the scattering amplitudes. And also, interestingly, they can be used to uncover structure and reveal symmetries of our theory. And because of this, they lie at the interface between particle physics, mathematics, string theory, and so on. So if we now focus on string theory, in flat space, we have a very well-established setup, which is a perturbative setup. And in principle, we can write an endpoint amplitude in terms of this worldsheet description. So we will be using two parameters, mainly. We have GS, which is the string coupling constant, and by tuning this to 0 and then keeping corrections, we are really doing the genus expansion of the Riemann surface. And then we have alpha prime, which even if it's not evident here, is in the Polyakov action. So alpha prime is just information about the size of the string. So as we change alpha prime, we are accessing different energy regimes of the theory. That's what we'll do later. When considering scattering processes, we sum over all the possible configurations of the worldsheet with increasing genus. And very interestingly, there are some cases where the sum is dominated by saddle points, so you can actually do the sum exactly and gain a lot of information about the theory. And we will go back to this point in a bit. Now, an outstanding question is, what about curved spacetimes? If you try to generalize the standard formulations that you have in flat space, it is very difficult to do it in general. So in principle, you would still have the perturbative genus expansion, but even at tree level, there is no direct worldsheet approach available up to now. So it was very interesting to look for another way to study scattering of strings in AdS or like general curved spacetime. And the lesson to learn is that we need additional tools to do this. And our best friend for today is going to be the AdS CFT correspondence, because that allows us to actually study string scattering amplitudes and AdS from CFT correlators of the dual boundary theory. So we will be using standard CFT techniques together with some indirect tools that we can learn from different areas of physics and mathematics. And the strategy will be to combine the worldsheet intuition that we have from flat space with alternative powerful tools, as I was saying. Before doing so, I wanted to give some motivation also behind our choice of studying high energy limits in general. So as I told you, alpha prime is one of the two main parameters of string theory when you study scattering. And as you take alpha prime to 0, you're really taking the size of a string to the point particle limit. So you have the field theory limit. On the other side, you can take alpha prime to infinity and study the very stringy behavior, so this high energy behavior. And if you go back to the 80s, where Gross and Mendel did the very first papers about string theory in the high energy limit, the motivation was to explore the mathematical structure of string theory by formulating equations and carrying out computations that prove the theory in different regimes. That's more or less what we did for the AdS Virasoro-Shapiro amplitude. We studied two regimes, the energy limit and the Regge limit. And just as an outline, the energy limit is defined by taking very large energy. So if you think about the Mandelstam variables, you will take S large, T large, while you keep S over T fixed, where S over T is like the scattering angle of the process. In QFT, We know also that the short distance behavior of the theory plays a crucial role. For example, we are used to the OBE expansion, the RG flow that are concepts in this setup. But what about string theory? So we'll try to investigate also this question later. And another important point that was known a long time ago about the energy limit of string scatterings in flat space is that the result is universal in the sense that it is independent on the quantum numbers of the scattered particles. And a very important point for today's talk is that the energy limit is a regime where you can do exact computation, and somehow this allowed us to make contact with the string worldsheet, at least classically, as we'll review. On the other side, the Regge limit is much richer because it contains full information on the intermediate operators. And one of the big achievements of Regge theory was to determine the answer in the Regge limit without knowing the full amplitude. So there is a lot to learn from these limits, and we will go back to this for the AdS case. So the two main goals of the AdS Virasoro-Shapiro program, in my opinion, are first, to learn how to analyze and include curvature corrections around flat space in an efficient and systematic way. And on the other side, we want to exploit and emphasize the interplay between string theory and some special number and functions that appear in number theory. And the main objective of study is the paradigmatic example of scattering of 4 graviton states at 3 level. In flat space, this is known as the Virasoro-Shapiro amplitude. And from the worldsheet perspective, it is given by this kind of nice integral. So what you do is to factorize out the information on the polarization vectors and then focus on the reduced correlator. So if you remember what I told you at the beginning, when you study scattering processes in string theory, you have the worldsheet topology. At 3 level, you have just a sphere. So here Z can be thought of as the cross section of the sphere. And then S and T are the Mandelson variables. An important observation that at the moment is just a mathematical observation but will be very relevant in the following is that if you look at this integrand, it is a single valued function of Z. So if you move around the punctures on the sphere that correspond to the vertex operators for the initial and final states, the integrand stays single valued. Now we go to AdS, and the setup where we can do computation is AdS5 S5, because through the AdS-TT correspondence, we can map the Virasoro-Shapiro on AdS to the correlator of four stress tensor multiplets to leading order in the large central charge limit, which is the usual dictionary in AdS-CFT. And we will see that in our program, we always do a chain of integral transform to define the AdS analog to the Virasoro-Shapiro amplitude. First, we go to Mellin space, which is something that we are used to, because in Mellin space, the correlator looks more like an amplitude. But our proposal is to do a step further and then go to Borel space. And I'll try to motivate this later. But the Borel transform of the Mellin amplitude will be our working definition of the AdS Virasoro-Shapiro amplitude. So the key takeaway from this motivation is that in flat space, we can use the worldsheet theory to compute string amplitudes, while for curve backgrounds, we do need additional tools. And before showing you our results for the Virasoro-Shapiro amplitude in AdS, I would like to make a digression on the interplay with numbers theory, which I find particularly fascinating. And we start from a very general problem, which is the one to really reveal and understand the hidden mathematical structure of scattering amplitudes in field theory and then in string theory. If we start from scattering in QFT, we know that we have a very well-defined setup, which is a perturbation theory. So you think of the amplitude as a sum over Feynman diagrams. This is a very easy case, but as you go to a loop level, you will see the appearance of complicated functions with branch cuts. This basically corresponds to the intermediate virtual particles going on shell. One possibility is to study these loop integrals from a purely mathematical and algebraic point of view and see what we can learn from the structures that we have there. And here I reported two very basic examples of loop computations in Feynman diagrams. And just to appreciate that rational functions are not sufficient to write down the answer. So as you can see, we can appreciate the appearance of zeta values, which is just the Riemann zeta function at integer values. as well as powers of logs and generalizations. And we'll go back to this. So what we want to learn from this is that in QFT, we need to go to loop level to see special numbers and functions in loop computations. If we now go to string theory, today we will focus on the closed string theory subsector. And at tree level, it can be shown that any amplitude in the closed string theory sector can be written in terms of these building blocks. So you have this kind of integrals which look very much the same as the one that I showed you before. And indeed, if you choose these parameters to be 1 and -1, you reproduce exactly the Virasoro-Shapiro amplitude, but you can actually reproduce also other closed string theory amplitudes at genus 0. Now we can do more, and we learned before that alpha prime give us access to different regimes of the theory. So even from just a mathematical point of view, since this is a function of S, which contains alpha prime, we can study the global and local properties of this kind of integrals, and we will see again the appearance of zeta values, polylogs, so special functions and numbers, but importantly, the only possible outcome is that they are single-valued special functions. And the thing that I want to remember for the following is that if you study the low energy expansion of this kind of integrals, so you take alpha prime to 0, the parameters of this asymptotic expansion will contain some very special numbers that are the single-valued version of the zeta values that I showed you before. This is technical, but we just need to remember this key point to appreciate then the result for AdS. And in 2 minutes, I'll try to just present the special function that we will be working with. We start from the classical polylog, which is a generalization of the log. It can be defined by this convergent series on the unit disk, but then you can actually extend it to the whole plane by an iterated integral representation. An important point is that once you evaluate it at z equals to 1, that gives you a definition of the zeta values at n. So this will be very important. One thing that you can do in mathematics is to do the multiple version of the function. So if you now think of this ln labeled by a word, so not just n, but a word of letters in some alphabet, it will be a function of a single variable, but now labeled by the word w. And we call this the length of the word weight. The only important thing is that these are special functions that are solutions to these differential equations. And again, if you take these multiple polylogs at 1, they define for you the multiple zeta value. But I just told you that as you study closed string theory amplitudes and you do the low energy expansion, you expect the experience of single valued functions. So one thing that you can notice is that as the log is discontinuous on the complex plane, so are the polylogs and the generalizations. So for example, you can show that this is the discontinuity for the classical polylog across the cut. So polylogs are special analytic functions of a single complex variable, but they have branch points. It means that they are multi-valued functions on the complex plane. And luckily, we can play a bit with this function and then take different combinations of polylogs such that the branch cuts cancel, and we define single valued functions on the complex plane. One very easy example is the log itself. So if we take the log of z and we add log of z bar, then the discontinuities are canceled, and this is the single valued version of the log of z. So you can do this game even for the multiple version of that. And this is what we call single valued multiple polylog. Sorry for the very long name, but it is what it is. And again, once you take that to 1, that will define the single valued multiple zeta values. And these are the kind of numbers that are the only possibility in the low energy expansion of closed string theory amplitudes. On the other side, we have our program that I would like to introduce you to today. And our proposal is to think of the AdS amplitude as an expansion around flat space. And each of these corrections around flat space will be given in terms of some worldsheet-like integrals. And the proposal is that the space of functions for these corrections is the single-valued multiple polylogs, as I will try to argue in a second. So let's look at this Virasoro-Shapiro amplitude. In flat space, if you remember the worldsheet integral that I showed you before, that can be easily done, and the result is this famous ratio of gamma functions. Interestingly, actually, Virasoro didn't know about the worldsheet description. He just guessed this answer by starting from the key properties that an amplitude should have. For example, that it should be crossing symmetric in the three Mandelstam variables, and it is. And also the polar structure that you should have. For example, you can fix T and vary S, and that will give you the poles at the mass of the tachyon and then higher states of the closed string. Then you can investigate different regimes. So you can study the low and high energy by tuning alpha prime, which in this representation is just encapsulated in the Mandelstam variables. I told you that the low energy expansion is a fundamental point to make contact with the worldsheet description. And indeed, what you can do is take this ratio of gamma function and take the low energy expansion. So now what do we expect for this? Alpha prime to 0 is really the point particle limit. So when alpha prime is 0, you just have the supergravity solution, the usually 1 over STU. But then you will have an infinite tower of stringy corrections, which is parameterized by these coefficients here. A very beautiful but maybe less appreciated representation of the Virasoro-Shapiro amplitude is the following. So you can show that this is equivalent to the ratio of gamma function, but it is interesting for our program because the coefficients are explicitly zeta values at odd integers that from number theory are the only possible odd zeta values. Even if we want to forget about this technical point, the nice thing is that this reflects the single-valued nature of the integral representation. So the two key takeaways that I'd like to keep for the following are that first, when you study scattering amplitudes in QFT, you need to go to loop level to see the appearance of special numbers and functions, while if you look at string theory, already at tree level, because of the infinite number of vibration modes in string spectra, you will have these special numbers and functions appear. And the second point is that the low energy expansion of closed string amplitudes contains only single-valued multiple zeta values. So let's try now to use what we learned to compute string amplitudes on curved backgrounds where we lack a worldsheet technology in general. And before introducing to that, I would like to ask if there are any questions. Can I go? Okay.
I guess not. You can carry on.
Okay, thanks. So let's now define the AdS version of the Virasoro-Shapiro amplitude. We'll be using the DSCFT correspondence. So in AdS, we want to study the scattering of massless strings. We have 4 gravitons on AdS 5 cross S5, described by type 2B superstring theory. The important thing to know is that we don't know how to describe perturbative string theory, how to quantize perturbative string theory on this background. But in our favor, we have the correspondence that tells us this is the same observable as the correlator for stress tensor multiplets in Mellin space. And here I reported the basic dictionary of the correspondence, which is the way that these two theories talk to each other. So on the DS side, we have capital R, which is the radius of a DS, and we will be taking it to be large because you want to look at flat space and then correction around flat space, which will be something like 1 over r corrections. But we also have alpha prime, which is related to the size of the string. On the other side, we have this capital N, which is in this case just the rank of the gauge group SUN, and we take it to be large. So by taking large N CFTs on one side, we are really studying weakly coupled strings in AdS. And then we have the square root of lambda, which is related to the 't Hooft coupling in super-Young mills. Our proposal is to do an actual further step and do a Borel transform of the Mellin amplitude. So this is the integral transform that is known as Borel transform. And even if it looks something exotic, it is not at all. Indeed, if you just skip the leading term in the 1 over r expansion, this is the implementation of the flat space limit introduced by Panedones in Mellin space. our proposal is to keep the 1/r corrections to that formula as working definition of the Virasoro-Shapiro amplitude in AdS. So when I will be talking about the AdS Virasoro-Shapiro amplitude, I really mean the Borel transform of that. And then in principle, one would need to go back to do the inverse transform to go back to Bellin space. This is nice because in flat space, it reproduces on the nose the Virasoro-Shapiro amplitude in flat space, the ratio of gamma function, and then we have a tower of curvature corrections that we want to build now, without having a worksheet description, as I was saying. So to sum up, in AdS-CFT, what we are looking at is, in AdS, we want to investigate the analytic structure of the amplitude of this for graviton states. On the CFT side, we want to look at the operators that can be exchanged in planar inequals for super Mills. And in principle, these operators are a prime target of integrability. So once integrability computes that for us, we can go back and know more about the amplitude of the AdS Virasoro-Shapiro. And then what Fernando and Tobias a couple of years ago thought was to use single valueness, which was a key property of string theory in flat space, also in this setup. And it turned out that not only that fixed almost completely all the curvature corrections, but it made also the worldsheet picture emergent. And by single valueness here, I mean the same single valueness that I told you before. So they assumed that once you take the low energy expansion of the curvature corrections, you still have the same special numbers that you have in flat space. And this turned out to be extremely constraining. So they used 3 key points to fix the answer. First, if you remember the ratio of gamma function, in flat space, the amplitude has just single poles because it's the gamma function at negative integers. But if you go around flat space, so you look at the AdS, you can show that you actually have higher order poles. So if you take, for example, the first correction around the AdS, you will have quartic order poles down to regular, and they jump by 3 as you take higher order corrections. So that's the first point. The second point, which was actually an assumption, is that the low energy expansion has still the same kind of coefficients as in flat space. And the last point is that we still want to make contact with the worldsheet description. So the proposal is to take the worldsheet integral from flat space and now add something more, which tells us that we are in AdS. So we want a function which is single valued because we want to reproduce single valued numbers. The proposal that they made is, as I was spoiling a bit before, is that these functions are the single valued multipolylogs, because number theory tells you that if you integrate that, it will reduce to single value multiple zeta values, which is the numbers that appear in flat space. So that is all about our program. You have this proposal for the Virasoro-Shapiro amplitude in AdS in terms of genus 0 worldsheet integral, exactly as in flat space, but now there are more insertions that are these special functions that I was telling you about. So while this is a very nice proposal for the structure of 3-level amplitude on AdS5 process 5, this is not yet the result of a direct worldsheet computation, which is by now unavailable. So single valueness plays a fundamental role in the construction of AdS scattering amplitudes as in flat space. And as a strong evidence for that, if you assume that these functions are the same as in flat space, they managed to extract the CFT data and compare with localization and integrability for planar and equals for super Mills, and they matched perfectly up to the order that we have in literature. The big goal of the program is to determine the amplitude to all orders in 1/r, but while we dream about this, we can focus on more accessible limits. That is going to be the second part of the talk. So what we want to do now is to look for regimes where we can make connections to more direct worldsheet computations. And so our proposal is that the natural next step towards the worldsheet theory is to investigate the high energy and Regge limits. So now we'll present our results for these 2 limits. You can also just forget about everything that I said and just remember the structure of the answer, but it is really two independent computations now. Okay, so let's start from the high energy limit. In flat space, we take the ratio of gamma functions, and you want to take the large energy limit. So S large, T large, S over T fixed. One easy thing that you can do is to use the Stirling's formula to access the energy limit, and you just plug it instead of the gamma function, and you obtain this soft exponential behavior. This is a very important result for string theory in flat space, back to the 80s, as I was saying, and very different from what you would have in QFT. The exponential behavior is universal in the sense that it is independent of the quantum numbers of the particles scattered. And Gross and Mende understood this universality in terms of the same kind of universality of singularities of the OPE that we're used to in field theory. But beyond that, what's important is that we can get this result also from the worldsheet representation. So we start from the worldsheet, right? That's the one in flat space. We want to take large S and large T. What we can do is to use the saddle point approximation. So you can solve for this integral in the high energy limit by just evaluating the integral on the saddle point, which turns out to be S over S plus T. And if you use this, you reproduce, of course, the one that you expect from Stirling's formula. So now what about AdS? In AdS, I told you that we have the same kind of integrand, but with slightly more complicated insertions of WK now. Important point is that these corrections in terms of S and T are just polynomials. So if you look at this, what we are doing is really just inserting polynomials in S and T. So it means that the location of the saddle point cannot be modified in the 1 over R expansion. So we still have the same saddle point in AdS. So you can just take the proposal for the worldsheet description and evaluate it on the saddle point from flat space. And to be completely honest, what we are doing here is to keep the leading large energy contribution at each order in order to be able to do computations. So our regime is to keep R large, so look at flat space and then corrections around flat space, large S, but we also keep S over R fixed. So it's not the usual very high energy limit, it's the energy limit around flat space. It would be nice also to go beyond that, but this is an open question. If you go back to flat space for a second, what we can see is that you can study high energy even from the point of view of space-time. In the very first slide, I told you that scattering amplitudes in flat space are represented by this integral representation, the path integral. So we have the Polyakov action, that is the one that I wrote before, e to the minus s, and then the insertions of vertex operators that take this form. At high energy, you can show that the path integral is, of course, dominated by a classical solution, and Gross and Mende found that the classical solution that dominates this path integral is this one, and doesn't come as a surprise that it is single valued as you move around the punctures on the worldsheet. So we have this single valuedness even from the space-time point of view. The next step is to plug this classical solution into the path integral, and you can check easily that you reproduce again the exponential behavior of before. So what we can do for AdS using the same kind of approach. The easiest generalization is to use embedding coordinates. So we just add one other index and we put by hand the Lagrange multiplier that tells us to take the contraction xm equal to minus r squared, which is the usual description of AdS in embedding space. So this is exactly the same as before. We are just putting by hand the Lagrange multiplier that tells us that now we are in AdS with d dimensions in space-time. The expectation, as in flat space, is that the energy behavior of the amplitude is captured by classical solutions, but now in AdS. And indeed, we developed an algorithm that I will skip because we want to focus on the Regge limits. But what we can do here is to look at this Lagrange multiplier, solve for x0, plug it into the Lagrangian and take the larger limit. Then what you do is to solve for the equation of motions in a 1/L expansion. And what we found is a schematic expression like that, where again, these L are made in terms of single valued multiple polynomials. So there is an algorithm that once we know the flat space result at high energy, tells us how to build all the tower of curvature corrections. Then, as in flat space, you evaluate the action on this classical solution and you reproduce the exponential that we saw before. Actually, our prediction is that curvature corrections exponentiate. So if you require the computation from the worldsheet perspective to agree with the computation from spacetime, we see that this is possible, and that is the answer. So the full high energy limit to all orders in S/R fixed is determined by the subleading exponent, which, if you remember, is just the first correction around flat space on the saddle point. It's a very cute and compact formula that tells you that we still have the same exponential behavior, but on the top of that, we have these curvature corrections that exponentiate. And in this sense, high energy limit is a regime where the amplitude can be computed to all orders, and that through this classical scattering computation allows us to make direct contact with the worldsheet description. Now the question is if we can explore a richer limit and relax some assumptions that we have in the energy limit. And that's what we did, and this is going to be the last part of the talk. So first of all, let me give you a bit of motivation about why Regge limit. I say some words at the beginning, but let's go back to that. We know historically that Regge limit is very useful in the presence of infinitely many resonances in scattering amplitudes. And this is a very well-known story about QCD and string theory and how it all began. But more importantly for today's talk, in the past, Costa, Gonsalves, and Fenedones looked for a generalization to scattering to Regge theory to scattering in AdS, which was the conformal Regge paper. And this is very much similar to what we did in the first part of the paper, but just in another language, which is the Borel space. If we now focus on the example that we are looking at, the Virasoro-Shapiro amplitude, again, that is given by the ratio of gamma functions. So we expect to have infinitely many poles for the exchange particles. And these organize in Regge trajectories that I plot here. So we have the spin of the exchange particle L versus delta, which is just a non-negative integer, known as, if you want, the flat space string mass level. It just tells us that the Regge trajectories are linear and are like this. One of the biggest achievements of Regge theory that I already mentioned at the beginning is that you can compute the amplitude in the Regge limit without actually knowing the full result. And the only pieces of information that you need is the spectrum of the particles in the leading Regge trajectory, which is this one, and the cubic couplings with the external particles that in the CFT language will be the P coefficients. So for the Virasoro-Shapiro amplitude, these, from n equals 4 super mil perspective through the SFT, these are the Nocchi-like operators for those of you who work on this stuff, which are the prime target of integrability. So for us, it was also very interesting to look at the Regge limit because it allowed to talk to the integrability communities as well. So what do we expect for AdS, starting from what we know in flat space? We are again in flat space and want to implement the Regge limit. We implement this by taking large T and S finite. The main point that we want to remember from flat space in the Regge limit is that the exchange of a spin J state makes the amplitude scaling as T to the J. And for the leading behavior, that is the answer. So if you take the ratio of gamma function and you implement this limit, you will get this answer, where 2s minus 2, again, is the spin on the leading Regge trajectory that I showed you before. while this exponentially is just the fact that we are taking a analytic continuation with by giving t a small imaginary part. But what we want to remember is that if we exchange the spin j state, the amplitude will go as t to the j. So we want to understand which kind of corrections we expect from AdS now. And the key point is that in AdS, the structure of the amplitude is more complicated than in flat space from the polar structure point of view. We don't have single poles anymore. We have higher order poles. So the first correction, quartic order poles at most, then seventh order, and so on, which is like schematically written this way. And Regge theory tells us that if the amplitude has higher order poles, we expect logarithmic corrections of the form log of t to some power. And this power is fixed by the order of the poles. Since this is the case, if you think about the AdS amplitudes as a perturbative expansion around flat space, we expect that even for AdS, we will have always t to the j from flat space and then some logarithmic corrections in t. But now we want to understand how to get to this result and which kind of powers can appear here. So we start from Mellin space, which is our favorite space. And we know that the Mellin, we like Mellin amplitudes because they are very easy with respect to the position space. And the OPE structure of the theory tells us that the Mellin amplitude will be something like this. So we are exchanging operators of spin j and twist tau, and m goes from 0 to infinity, and you can see that for m non-zero, you're labeling the descendants of the operator. Then we will have some regular terms that will not enter the following discussion because in the Regge limit, they are just at most polynomials of order polynomials like t to the j minus 1. But we want to look at the leading Regge limit, which is t to the j, so we'll just forget about the regular terms. Another important fact is that since we are working with the SAT, we have some constraints on the Mellin amplitude for the 4-point function, and we want to satisfy always this identity, which has been used in our paper. So this is tau and j that appears here, but on the other side, we have the mass and the radius of the bulk theory. So that's the way that two theories talk to each other. Now, the residues of the poles are known as Mach polynomials and in general are very difficult, but they are actually particularly simple in the leading large T behavior, and they are for some choice of normalization, they just go as t to the j, exactly as in position space. But now t is the understand-like variable in Mellin. So we expect to have something like this when we study the Regge limit in Mellin space. So now we have two options. We could compute the exchange amplitude explicitly in this limit because it is quite easy. We choose not to do that and focus on a difference equation that the amplitude satisfies, which is something that we do often in mathematical physics, because if we find the difference or differential equation for some unknown quantity, then you can work at the level of the equation to gain in Mellin space. So in principle, one would be able to recover the conformal Regge paper results by taking the Borel transform and mapping to our results.
So, sorry,
Can you go back a little bit because we lost connection?
we lost connection for a bit there. Could you go back just one slide, please?
Here?
One further?
Here?
Yes.
Yes. Could you just explain the last part again, please?
Yeah.
Yes.
Starting from we have two options, and then
Okay, great.
Yeah,
Sorry about that. Yeah, so I was saying that you could just compute the exchange amplitude in the Regge limit in Mellin space, but we choose not to do that. and instead we look for a difference equation that it satisfies. Because in mathematical physics, it's always very interesting to look for either difference or differential equations. And then at the level of the equation, we can gain a lot of information about the amplitude itself without really knowing the amplitude. So we choose to do that. And the proposal is to do this game, but in Borel space. So we just go to another space, and here you heard me.
So just one question. You have the tau shifted by 4. Is it because you're looking at the super conformal?
Yeah.
Not polynomial? Yeah. In the you have in the rest you have the not polynomial with the where you have tau, you have shifted by 4.
I think it is because you're doing the reduced Snelling amplitude.
Okay, so
and so you have the shift.
Okay, so it's related with a super conformal.
Yeah.
Okay.
Exactly. Thanks.
And
okay, so now we want.
Question is it comes from the Casimir or what?
This?
Yeah, the difference equation.
The difference equation is just from like the usual difference equation that you have in Snelling space, like when you shift S, for example. I think you can. It's the same as the Casimir equation. Yeah. So you apply that and then you collapse to a contact like being in Snelling space.
Okay.
Yeah.
Cool. Thanks.
Okay, so we do the same game but in Borel space. And we know that the first step in Regge theory is usually to analytically continue the partial waves as a function of the spin J. And I will just briefly review the same but in Borel space. So we start from this expansion, which is the limit, the Regge limit in Borel space. So we have the OP coefficient squared and then some partial wave, find objects NT to the J. But now we have capital T, which is the Borel transform. We write this sum over the spin as a contour integral, and that will pick for us the poles at even integers because we are dealing with identical external scalars. So up to now is the standard Regge theory. So we keep doing the standard steps with the form the contour, and it picks up the Regge poles that are close to the physical poles of the amplitude. In the large T limit, the pole with the largest real value of J dominates. This is because we are looking at the leading Regge trajectories, which is made of the operators of lowest dimension for each even spin. So this is nothing new. We just use Regge theory, but in Borel space. The novelty here is that, as we saw before multiple times by now, in a one-over-rad expansion, the Borel amplitude contains poles of higher and higher order. And the location and residues of these poles are determined by the difference equation that I was mentioning before, by in Borel space. So I will not write this explicitly because it's just technical, but it's important to know that we have a precise tool that tells us where to look for the poles and the residues. And in particular, the pole will be at J equal J star, which is the solution of this implicit equation. And since we know that it will have in the J plane, it will have a 0 at J star, we can factor out J minus J star and call everything which is left beta of J. This is just a streamlined denotation. The last step is to use our friend Cauchy's theorem, and we just get this simple, result, which essentially tells that for every pole of order K, we can write its contribution as the differential operator, like this. So we take derivatives with respect to J as we are used to in Cauchy's theorem. Formally, we can define this operator, so del J and 1 over beta J, which is defined by this equation. We call it Y, because at the end of the day, what we want is to do the same game that we have in flat space and write the amplitude in AdS in terms of the CFT data of the intermediate operators. So we just implement Cauchy's theorem in this new Y space, and our prediction is that the Regge amplitude is given by this nice compact formula, which as promised contains the CFT data of the exchange operators in this case in n equals 4 superunion Mills a strong coupling. So we have three key ingredients. First, we have this operator, R of y. Well, again, think of y as derivatives with respect to j. This tells us that we are not in flat space anymore, but we have the curvature of the background. Then we have the OP coefficient of the intermediate operators with the external ones. And finally, even if we want to forget about the exact expression of this number, these functions, these are the dimension of the operators in the leading Regge trajectory. So really, we just need the CFT data from integrability because R of y is given to all orders in 1 over R by the difference equation that I told you before. So to all orders in 1 over R, we have explicit solutions as derivatives because y is del j on the flat space result in the Regge limit, which is a check of what we expected because if you think of derivatives with respect to j, they eventually will hit t to the j. So that will reproduce the log terms that we were expecting. And we really have logarithmic corrections in the Regge limit. We can also gain some results to all orders because this is a perturbable setup. The natural thing would be to expand R of y 1 over R, and order by order you have an explicit expression for the corrections around flat space. But what about finite R? One thing that you can do in this expansion is to resum all the leading logs, all the subleading logs, and so on. You can resum all the leading logs, and this is the easiest part, and leading logs exponentiate, giving us this beautiful formula, which is very much like the high energy thing, and indeed they agree on in the right regime. We can do more, and we were able to resum also the subleading logs, and there is the resummation of the subleading logs. More deeply, this gives us an all-order result in the regime of large R and large T, where now you keep log cube of T over R squared fixed. So even if you were to resum even the sub-subleading contribution and so on, that would be relevant. So this is a very nice determination of the result in this specific limit. But even before the last step, this is again exact, and is a prediction of the amplitude. So morally, this is the same of the Mellin space result in the conformal Regge paper. We would need to Borel transform that to see that they are the same. But it's nice because we have an explicit way of building corrections. The last step is to see what we can learn now about the worldsheet. Because at the end of the day, we have our proposal that the corrections are given by worldsheet integral. So we want to understand if this tells us a bit about the worldsheet as well. And the answer is yes. So we start from the worldsheet representation. For the last time, I will remind you that it is the same as in flat space, plus more complicated functions that are polynomials in S and T and have transcendental weight 3k in Z. What we found is that if you want to implement the Regge limit at the level of the integrand, you just need to take this limit. So you are taking T to be large, of course, but you also have to rescale Z and Z bar to 0. So you take small z, large T, and morally you're keeping T over T times Z fixed. And this term is just to extract the leading Regge behavior. At each order in 1 over R, this G hat, which is the integrand in the Regge limit, is just a polynomial in Z, Z bar, and log of Z, because this has to be the case starting from single-valued multipolylogs, and we check that this works perfectly up to the order that we have results from integrability. There is a subtle point that I maybe can go back at the end, but I just wanted to mention that when you work with integrands, you have ambiguities, because you can always add stuff that integrate to 0. But the Regge limit was also a nice setup where to fix most of these ambiguities, but by requiring that once you take this limit, the integrand stays finite. So this tells you how to fix part of them. But we can also do something more interesting and reverse our logic. So now we forget what we know, what we propose for the Virasoro-Shapiro amplitude. We don't know about single-value multipolylogs. We just know from the other side of the computation the answer. So these derivatives of the flat space result. Now what we do is to look for integrands that lead to the correct result in the Regge limit to all orders, which is very nice, I think. So we take the usual integral and we insert a function of s and a function of log of z. It has to be a function of log of modulus of z because on the other side of the computation, we have derivatives that eat t to the j producing logs. And if we want derivatives, it means that you have to insert logs. Think about this integrand and we insert a log. This log is the same as taking a derivative of the first term with respect to j. So we really need the log of modulus of z in order to reproduce derivatives with respect to j. That has to be there from the other side of the computation. So what we can infer from our prediction is this functional equation for integrands that reproduce the correct result in the Regge limit. And you can solve for this functional equation and you find families of solution for the worldsheet integral that lead to the correct Regge behavior to all orders. This is very powerful because, again, this tells you that the answer has to be in terms of single-valued logs, which is a completely independent check that the answer beyond the Regge limit, it has to be single-valued and transcendental in Z. And as the final key takeaway slide, the DS Virasoro-Shapiro amplitude in the Regge limit can be written in terms of derivatives of the flat space result and admits an integral representation with single-valued logs, which is in complete agreement with the proposal of these curvature corrections at G0 integral. And I think I'll just conclude by doing a summary of what we saw. So the DS Virasoro-Shapiro program aims at to compute string amplitudes and AdS from AdS CFT, number theory, integrability, and importantly, from the worldsheet intuition that you can develop from flat space. One important point was single-valuedness that was used to understand on one side and construct on the other side scattering amplitudes in AdS exactly as in flat space. Crucially, the assumption that the low energy expansion contains the same special numbers as in flat space was really constraining. You can read in the previous papers that only from this assumption, they were able to fix completely the first correction around flat space and almost completely the second correction around flat space once you know the Konishi operator from integrability, which is super constraining. And to be honest, we don't understand single-valuedness. Like we know there is a mathematical evidence in flat space. We know that it's constraining here, but it would be amazing to develop more intuition behind that. On the other side is led us to make contact with the worldsheet description and make more direct comparison to a putative worldsheet description of strings on AdS5 process 5. Even if it is like the most paradigmatic example and it is easy because it's a maximal supersymmetric case, alpha prime correction are extremely challenging to compute. So it was nice to develop an alternative point of view. And the further step towards the worldsheet theory was the high energy and Regge limit. And what we learned from the high energy perspective is curvature corrections exponentiate in this leading large energy behavior. And this can be reproduced exactly from a just bosonic model describing scattering of classical strings on AdS. In this sense, the result was universal as in flat space. On the other side, we saw the Regge limit, and we have a similar exponentiation. So leading logs exponentiate, and then we have some sub-leading corrections. And I mentioned this already, but let me stress one last time that it is nice to look at the Regge limit because it can make the bootstrap and integrability communities interact more because of the Konishi-like operators that enter the game. But importantly, from the worldsheet perspective, Regge limit independently make manifest single valueness of the integrand at z equals 0 because it tells us, given that we know the correct Regge limit, you need to input an integrand which is a polynomial of log of modulus of z. So the natural step now that we haven't investigated yet would be, what if we now take Regge limit, which is the same as single valueness at 0, and we add single valueness at 1? Will it be enough to get the full amplitude. And I think Fernando's student checked that this is the case for the first correction, and we are trying to understand if this is the case even beyond that. And given all this information that we can gain by probing the theory in the energy limits, it seems, and I underline seems, that the full amplitude is now within our grasp. But of course, there are a lot of open questions and a lot to be understood deeply. And I think I will just conclude here and thank you for your attention.
Okay, thank you very much, Maria. Great talk. So, are there any questions?
Yeah, I have a couple. So, is it important for you to use dispersion relations or not?
I think the information from dispersion relation is the same as saying that you have higher order poles. The residues there can be mapped to, yeah, the dispersion relation. I think they used that at the very beginning. But once you say this is the order of poles that you have, I don't think they used it more. At least up to now. But definitely did at the beginning, yeah.
That order of pole couldn't it follow from okay, I'm exchanging some operator in the OB and then I impose some correction and then since exchanging one operator in the OB corresponds to having a single pole. And then if you have corrections, that single pole, since you are correcting the denominator of well, you're correcting the denominator, that will lead to higher of the pole.
Yeah. So yes, exactly. The polar structure will tell you about like anomalous dimensions and corrections to the operators. Yeah. But I think, I mean, we didn't use this at all for the high energy and Regge limit, but to do the proposal at finite energy, they definitely use that.
Yeah. What about so was it crucial to assume the multiple that the amplitude comes from as a multiple? Well, the basis is a multi-polynomial. But why couldn't you use? Well, there are marginal functions. Why couldn't those appear?
Sorry, which kind of functions? I couldn't hear.
Marginal functions like.
Okay. I think this was just the easiest function that upon integration over the Riemann sphere reduced to the multiple zeta value. And then we assume that you still have maximal transcendentality. So you always have the same weight and just single value multipolylogs or single value multipolylogs times the zeta values of the proper weight. You could plug more complicated things, but it seems that this space of functions is good because it reproduces all the integrability and localization results. But of course, there is no direct worldsheet motivation behind that. Like, could be something more complicated as well.
Yeah, I guess that usually happens at, well, at least in the other spectrum of the coupling. When you look at weak coupling, you look at 1, 2, and 3 loops, then everything seems to follow following that for those functions. But once you go to higher order, to higher loops, then more complicated functions show up.
I agree. Yes. Yeah, definitely. It would be nice also to go to higher genus and see what happens.
Yeah, right. Okay, I guess now Philip has a ton of questions.
No, a ton of them have actually been answered already. I do have one question.
Philip, you only have half an hour.
No, this is right. This is not a lot. It's about the exponentiation of the curvature corrections. Well, this is very characteristic that you had an exponentiation of the classical action in a high energy limit. Isn't those curvature corrections just a statement that you can expand your AdS action into flat space curvature corrections? Were you surprised by the result?
Sorry, say again?
Was that a surprising result that the curvature corrections exponentiated?
I think so. To have the exponentiation, you need to fix S over R. So it is not exactly the energy limit, which is just take S large. You are sending S and R large, but simultaneously, if this makes sense. If you didn't do that, that would be more complicated. And if you do like a non-S classical scattering in AdS at finite R, I don't know if you would still, I don't think you will still get the exponentiation. You would have corrections, and there are groups working on like minimal surfaces problems that are similar to this classical scattering, but I don't think this can be mapped to our result because there you really need to relax the assumption of S over R fixed and do the real high energy limit in AdS. Our game is more you look around flat space and you take large energy, but that's why you have curvature corrections exponentiating. It would be nice to understand this better, like what is the physics behind the exponentiation, but it is something that happens a lot of times in physics, yeah.
So you're not exactly studying the iconal limit, but it's since you're fixing that ratio, you're still having it.
Yes, you keep, so to all orders in one of R, you keep the leading large energy, but yeah, so it's more around, so it's closer to flat space than AdS. That is the first step. Like it still gives a lot of constraints. It would be amazing to do more, like to include more corrections by having S over R small, but it's difficult. Like it's difficult to do computations, to do the equation of motions and all this stuff. It's something on the to-do list for sure.
And what about the universal structure of the Regge? Can you go back one slide?
Yeah. Like here,
the leading logs exponentiation.
So let me go back.
It's there. I got
Here.
Yeah, exactly. So that's also a result that one expects the Regge limit having a very universal behavior, and so it's kind of the same question.
It is the same question. I think here, up to this point, you are doing the real Regge limit, and then you say, okay, once you resum the subleading logs, then it is the all order result in the limit where log 2 of the over R squared is fixed. But yeah, this is like, it agrees with the energy result in the right regime, and it is really something like universal if you want. I think whenever you have exponentiation, there is a lot to understand, but we haven't explored this further yet.
Okay. I think the other questions have been answered as you gave the talk.
Okay.
Question 3.
I have a quick question. At some point, you transferred from the Mellin space to the Borel space. How exactly does that play into this whole program?
Sorry, what?
At some point, you transferred from the Mellin space to the Borel, right? So how exactly does the Borel plane help with the analysis that you're doing?
Oh, it's just an easier space where to look at, because, so let me go back. Okay. I will find it. In here. Okay, so that is the Borel transform. And I think it's just like that you can do integrals in an easier way, and you have a clearer way to map to the worldsheet perspective. Because at the end of the day, you do need to implement Borel space to get the flat space result. So the ratio of gamma function is really mapped to the Borel answer. And then it's just a proposal for as a working definition of the curvature corrections. I think you could try to do the same in Mellin space, but it would be a bit more difficult, especially like in the high energy. It seems that once you go to this space where S and T are given by these ratios, it was nicer in terms of like functions appearing. I wouldn't know how to quantize how easier it would be with respect to Mellin.
I see. Okay. Yeah. Thanks.
Yeah, thank you. And one thing that I forgot to mention is that in order to make contact with the worldsheet description, you need to resum the low energy expansion. And if you try to do this in Mellin space, you fail, because the low energy expansion of the Mellin amplitude is as a radius of convergence 0. So what's nice about Borel space is that it makes the sum convergent and it removes the gamma that is problematic. So maybe that's a good way to see that.
I see. Yeah, thanks.
Thanks.
Any more questions here or at home?
Yeah, great talk. Just a simple question. You have this result of all orders in 1 over R. I think you said it at some point, but now if you have that, then you go from Borel back to Mellin space, you should have the conformal Regge theory story. Is this some check you did, or?
We didn't yet. We will do that, but it's very complicated because the functions appearing are extremely cumbersome. So to do the actual inverse integral transform, I think it will be difficult. But the prediction, I agree. So at least it's a check.
Okay, good. Thanks.
Thanks.
All right. So there's no more questions.
I do have.
Okay.
So are you expecting, like, once you do this, it's a continuation of Joel's question, I think. You're expecting that once you do this inverse Borel transform to get the Mellin amplitude, you will have the Regge story. So is this interpretation correct, that the 1 over R corrections are correcting the linear Regge trajectory? So the corrections are seen as like curvature in the linearity of the Regge trajectory?
Yeah, I think you have logarithmic correction to this to the J, essentially. And the claim of the conformal Regge paper, I think, is that you can map that to the position space result. So in certain sense, you are doing, log correction to T to the J. But I would need to actually do the transform to see how complicated they are in Mellin.
Yeah.
You still have like linear trajectories, I think. And then this log of T with some power coming from the order of folds. I think Vasco can knows more about me about this. I am not sure what would happen in Mellin. Like if you can see these logs explicitly, I don't think so.
Okay, then there's no more questions. Well, let's thank Maria again.